Hi there. Today we are going to discuss homogeneous differential equations of the second order. The method that we are going to discuss is not limited to second order, it can be extended to higher order, but we are going to focus mainly on the second order. So we will go over a special case where the differential equation has constant coefficients. We will cover examples and also provide you practice problems. So the standard second order linear ordinary differential equation has this form, where the left-hand side of the equation tells that this equation is a linear because we have px and qx, they are function of x and they are not function of y. And the right-hand side equals to 0 makes it a homogeneous differential equation. If it is not equal to 0, it's not going to be a homogeneous. So it is required that we need to have a 0 on the right-hand side, and the left-hand side must have this form. If that is the case, then the solution can be obtained by linearity or superposition principle. What it means is, to get the general solution, all we need is two possible solutions. If somehow we are able to figure out two possible solutions to this equation, we can combine them and we can come up with the general solution. And the general solution is going to be of this form, C1y1 plus C2y2. Please note y1 and y2 must be linearly independent, meaning you cannot take the y1 and y2, which are kind of same function, and you're multiplying them with the constant. That may not be the appropriate. So it's a requirement that we need to have y1 and y2 be linearly independent. They should be different functions. And in that case, we are able to combine them and come up with the general solution. Now, once we have the basis of solution, this method is straightforward, and we will go over a special case with a constant coefficient where we'll talk about how to find those basis of solutions. So to solve these differential equations, we need initial value and also we need a known derivative. These are the two requirements. If you need to have a function value and the derivative value, only then you will be able to solve the second order linear differential equations. If you have just two functions values, you won't be able to solve the differential equation. Let's go over a quick and simple example here. We have initial value problem. We are given with the initial conditions, derivative and the initial value. Again, since we have both information, we should be able to solve this differential equation. And we are also provided with the basis of solution, sin x and cos x. And in this case, since we know the basis of solution, what it really means that sin x is the solution to this differential equation. In fact, if you take the second derivative and put it here, you will get it equal to 0. Same thing with the cos x. Cos x is also the solution to this differential equation. But our goal is we really want to find the general solution, all possible solutions that will satisfy this condition. Not just one of them, but all possibilities. So for that reason, we need to look for what would be the general solution. So the general solution of this problem, since we know the basis, would be C1 cos x plus C2 sin x. And we can find these constant based upon these conditions. So to apply these conditions, we need the derivative. So let's take the derivative. Y prime equals minus C1 sin x plus C2 cos x. Now we have function and the derivative. We can substitute these values and we will be able to find out the constant. If I substitute x equals 0 and y equals 3, what we get is C1 equals 3. For the second equation, the derivative equals minus 0.5 when x equals 0. If I substitute it, we get C2 equals minus 0.5 because we know cos 0 is going to be 1 and sin 0 is going to be equal to 0. Now, since we have the constant, the general solution for this differential equation is going to be 3 cos x minus 0.5 sin x. Now, in this particular problem, we knew what the basis of solution was. But again, in certain cases, we may not know the basis of the solution. But in one special case where your differential equation happens to have a constant, there is a special method that we can follow. And that is if, again, that's what we are going to discuss now. So linear ODEs with a constant coefficient, meaning now A and B, these are the constant, they're not a function of x. And if that is the case, what we can do, we can write a characteristic equation assuming the basis of solution is some e to the power lambda x. So if I substitute e to the lambda x in this equation, what we get is a characteristic equation, which is lambda squared plus a lambda plus b. So essentially what we do is we take this differential equation and replace y with 1, y prime with lambda, y double prime with lambda square. Again, if it was higher order, if it was y triple prime, then you will have the lambda cubed and so forth. And we solve that equation for lambda, and these values of the lambda become the basis of the solution. In this case, you get 2 lambdas, so it will be e lambda 1x, e lambda 2x. These are going to be two bases of solutions. And now we have the basis of the solutions. We can follow the method that we just discussed to find the constants based upon the boundary condition. A few things to note, since we have two roots for this equation, and it is a quadratic equation. So we can have a real root, we can have a double root when this equals 0, or we can have a complex root. Depending upon where it falls, we have a different form of the y. So y, again, it could be two distinct root, that would be the simplest case, or it could be a double root, or it could be a complex root. If it is complex root, then again this number a square minus 4b square root divided by 2 is omega, and minus a over 2 is the number that we have here. Now let's apply this to example. We have a motion of mass spring is described using this differential equation, and we want to solve the differential equation, meaning we want to find the displacement as a function of time. Now, to solve the differential equation, we would need initial values, and we have a displacement at t equals 0 is 1 meter, and velocity is 10 meter, which is the derivative, it's a dx by dt. So we have two required conditions. We have the initial value, the value of the function, and the derivative. So we should be able to solve this differential equation and have x as a function of time. The first step would be we will write the characteristic equation. So we see lambda square plus 25x becomes 25, because remember x is going to be replaced with 1, x derivative is going to be replaced with lambda, x second derivative is going to be replaced with the lambda square. So we have lambda square plus 25 equals 0. This gives you lambda is actually an imaginary number, 0 plus minus 5i. So imaginary component is 5, real component is 0. Following the three conditions that we have, it is a complex root. So we will follow the third case, and our equation will have this form: e to the power minus a over 2t and a cos omega t plus b sin omega t. And omega is going to be 5 for us, and a over 2 is going to be 0. And if I put that back, I get y equals a cos 5t plus b sin 5t. Now we have the form of the solution. Now we have to find out a and b. Once we have a and b, problem is solved. So to do that, we will satisfy these two conditions. So displacement is known. Let's get the velocity, which is the dy over dt. It will be minus 5a sin 5t, 5b cos 5t. Now let's substitute when t equals 0, displacement equals 1. And when t equals 0, velocity equals 10. So we substitute the values t equals 0, and y prime is 1 and 10 respectively. And what we get is a equals 1 and b equals 2. And once we have a and b values, we have solved the problem, and our general solution is going to be cos 5t plus 2 sin 5t. We have two practice problems for you. The first one, initial value, where the basis of functions are known. The second problem, we are trying to use we will use the second method. It's a constant coefficient differential equation. I hope you found this useful. See you next time.